The legend Sir Isaac Newton was struggling for years to solve a problem that you and I will be able to solve in a few minutes using Maxwell's equations. I never really understood what the big deal about Maxwell's equations were until I read Feynman lectures. Feynman never fails to deliver. So the goal of this video is not just to understand the Maxwell's equations. A lot of videos does this, but instead it's to get a much deeper understanding of the first two equations. We'll focus only on the first two and use it to solve the problem that Newton couldn't for years. So if you're ready for it, let's begin. Let's start with Maxwell's first equation. So we start with Coulomb's law, which says that if the electric field at some distance r from a point charge will always equal q divided by 4 pi epsilon naught r squared, the inverse square law. And Feynman says, look at the denominator, Mahesh. Do you see a 4 pi r squared? Do you know what that is? And I say, yes, I know that. 4 pi r squared is the area of a sphere. It's going to be the area of this sphere. And so then we rearrange it to get this equation. We bring that 4 pi r squared on the left-hand side. And look, we already kind of sort of have a skeleton of our eventual law. Feynman says this is already a more elegant version of this. And I'm like, wait a second, how is this more elegant? We just rearranged it, right? So he says, look, this product, whatever that is a constant. It does not depend upon the size of the sphere. Look, if I make that sphere bigger or smaller, I will get the same answer. Q divided by epsilon naught. And I say, okay, but what exactly is this product? I mean, multiplying electric field with the area of a sphere sounds so random. Well, he says that, Mahesh, maybe that's not what we are doing. Probably what we're really doing is we're multiplying electric field with a tiny local area at that point. And then we're doing it over the entire sphere, and we're just adding them all up. It just so happens for our case, electric field is the same everywhere on the sphere because the distance is the same. And therefore, in our case, electric field pops out of that summation, and that thing in the bracket just adds up to give you the total area of the sphere, right? If you add up all the tiny pieces, you get the area of the sphere, which means in reality, what's happening, what we are really doing, we are doing a summation of electric field and the tiny local area at everywhere and adding them up. And that is equal to q divided by epsilon naught. And at this point I say, well, wait a second, Feynman, what do you mean by let's generalize this? Because this only works for a sphere, isn't it? And this is where he smiles and says, no, Mahesh, this will work for any shape. What? We just derived it for a sphere. We looked at the area of the sphere, Feynman. How can you say that this works for any shape? So, Feynman, are you saying that if I take some random close shape, and if I take the electric field at every point, multiply it with the tiny area, and then add it all up, I would still get E times 4 pi r squared? Feynman says, yes. I am intrigued, Feynman. How do you say that? And this was, by the way, one of the things that I felt like not many textbooks explained it, but Feynman's argument is beautiful. So how does he go about it? Feynman says, let's consider a tiny piece on the big surface that you have drawn, such a way that it sort of forms a cone with this piece over here with the charge at the apex. Now, he argues that if we can prove that the electric field here multiplied by the area here, if that product equals the product over here, electric field multiplied by the area over here, then we're done. Because then we can prove the same thing with the same argument that here the product should be equal to the electric field multiplied by the area here. And then we can do that over the entire surface, and prove that the electric field multiplied by the area is equal to the corresponding piece here, which means if you sum up the electric field multiplied by the area here, that should be the same as the summation of the electric field multiplied by the area here. That's the central argument that Feynman is doing. Just to be clear, what he's saying is that all we have to do is prove that E into delta A here is the same as the E into delta A here, and then we can do it everywhere, and then we can say that this works in general. For any shape, this will yield the same result. And I'm intrigued because we've taken a random shape. Feynman, how in the world are you going to prove that the E times delta A here is the same as the E times delta A here? Well, he says, let's do that. Let's concentrate. He asks me, well, Mahesh, what is the electric field here compared to here? I tell him that it's smaller, but I don't know how much it is. asks us to assume something. Let's say that this distance, this big distance, is, let's say, twice as much as this small distance, the radius of the sphere, okay? Now, how much is the electric field? Well, if you go twice as far from the charge, then because of the inverse square law, you get a 2r in the denominator, you get 4. And so the electric field goes down as 1 over 4. And so this electric field is 1/4 of this electric field, which means Feynman is saying that all we have to check now is if this area is 4 times as big as this area. Because then if this is true, we're done. Because the field has become 1/4, area has become 4 times more, so the product will be exactly the same as the product here. And so the question is, will this area be 4 times as much as this area? And Feynman says, no, it won't be. I mean, how can it be? It's a random piece that we have chosen. Look at it. It's not even forming a right circular cone. It's just creating some crooked shape over there. It's like a truncated cone. So it won't work. What's the point, Feynman? Why are you wasting our time? But Feynman says, wait a second. Instead of taking this blue piece, what if we considered a piece that actually completed that cone very nicely? Now look, he says, now look, if we have a perfect right circular cone, then because of, similar triangles, equivalent triangles, whatever that is, if this is twice as big as this distance, then this length, the diameter will also be twice as big as this diameter. In other words, the area over here will also be, area over here will be 4 times as much as this area, because area goes square of diameter. Which means if you consider this piece, then indeed it works out. The product of E and delta A will be exactly the same as the product of E and delta A. But I ask Feynman, what is that piece? That's not the piece that we are interested in. This is the piece that we should be looking for. And Feynman says, Mahesh, what exactly is this piece? This piece is actually the component of this area in the perpendicular direction to the electric field. That's what this piece is, right? Yeah. So this means, Mahesh, you're right. If you take E into that earlier area, the actual area, it won't work out. But instead, if you consider E into the perpendicular component of that area, it does work out. The perpendicular component does become 4 times as big as this. And if you take this product, indeed, it becomes the same as this product. Therefore, Feynman says, let's consider this product instead. Even here, for example, if you multiply E and delta A of this actual area, it will not be the same as E and delta A of this area. It will not be the same. But instead, if we consider the perpendicular component which forms the nice right circular cone, then that works out. That means we need to make a small modification. Feynman says, yes, I misspoke earlier. If you take E times delta A of the actual pieces, it won't work out. But instead, if you take E times delta A perpendicular, this is the perpendicular component to the electric field. If you take that piece, then it will indeed be equal to E times 4 pi r squared. And so let's consider that is what he says. And of course, a small detail is we shouldn't be taking big areas. We should be taking very tiny infinitesimal areas. So this will become a dA and the whole summation becomes an integral. But we've got it. All we are saying is that if you take E and multiply it with the perpendicular component of the area at that location and add it all up over the entire surface, then it doesn't matter how big that surface is, what the shape or the size is, it'll always equal Q divided by epsilon naught. Why? Because of this, just we saw. That's the intuition for it. That's the crux of Maxwell's equation. Isn't that beautiful? Just look at that. That's beautiful, right? Now at this point we should ask Feynman, well, but why does it turn out to be like that? What is that E into dA perpendicular? It's so beautiful, isn't it? And Feynman agrees, it is so beautiful. In fact, it has the properties of something that's flowing outward. Think about it. If you had a tiny sprinkler over here that's spreading out water, then the amount of water that goes out of this sphere would be the same as the amount of water that goes out of this surface. In fact, the amount of water that goes out of the sprinkler has nothing to do with what surface you choose. It has something to do with only the sprinkler, how the strength of that sprinkler. Isn't it something very similar happening over here? This product, whatever that is, it has nothing to do with the surface that we are choosing. It has only something to do with the strength of that sprinkler, the sprinkler being the charge. So in some sense, this product behaves very much like something flowing. Therefore, we give it a name. We call it the electric flow or the electric flux. For a long time, I never understood why we defined electric flux in the first place, why we defined it as E times the perpendicular component of an area. But now it makes perfect sense because it's that product that behaves like a flow. It's amazing, isn't it? All the hard work is done, folks. Now we just have minor things. First thing is we might ask Feynman, well, what exactly is this dot? And there's an arrow mark over here. And Feynman says, well, it's the same thing. Don't worry too much about it. It's just a fancy way of writing it. Mathematicians like to write it in a fancy way and just call it E dot dA. But it's the same thing. It just means you take the electric field, multiply it with the perpendicular component of the area. But it's the same thing, all right? We'll just write it in that fancy way. Secondly, what if you have another charge over here, Feynman? We have only considered one charge. Well, Feynman says, let's concentrate on just that charge for a while. If I want to know what's the flux due to this charge through this entire surface, we do the same thing as before. We're going to draw a surface, a sphere over here, and then we make all the same arguments that we did, and therefore the flux due to this charge will be Q2 divided by epsilon naught. And therefore, what will be the total flux due to this first charge and the second charge together? Hey, it's going to be just Q1 plus Q2 divided by epsilon naught. That's why we write that the right-hand side is the sum of all the charges that we find. But one last question we ask Mr. Feynman is, what if a charge is on the outside? What happens then? Well, Feynman says, we've done all the hard work. Let's use the same thing. If we draw something very similar to before, this time, again, you find the flux here should be the same as the flux here. Same argument of the electric field and the area thing. But here there's an inward flux and here there's an outward flux. They're both equal, which means the net flux becomes zero. In other words, this does not contribute to any net flux. And I can do the same thing over the entire surface. And therefore, if a charge is outside, its contribution to the total flux is zero. It doesn't contribute at all because whatever inward flux it gives the same amount of outward flux. And look, the sprinkler does the same thing. If there was a sprinkler over here sprinkling water, whatever water enters, the same amount of water exits. So the net water that exited due to that sprinkler is zero, which means when you are calculating the total flux, what matters is only the charges that are on the inside. And there we go in its full glory, the Maxwell's equation. We have it. We have it. We've derived it from Coulomb's law, but more importantly, with pure logic, pure intuition, and some brilliant arguments. Well done, Feynman. Well done. It's time to apply this. Feynman, what was that problem that Newton was struggling with? Well, Newton says, remember Coulomb's law. You know that Coulomb's law can be used for a single point charge, right? What if you have a ball of charge and you need to figure out the electric field at some distance or outside of it? How do you calculate that? Well, my first instinct is, can I just use Coulomb's law? Well, no, because it only works for a point charge. So if you have to actually calculate for the whole ball of charge, you have to take a very tiny piece, dq, calculate the electric field due to that, and then integrate over the entire sphere. And let me tell you, that integral is nasty. It's pages long. And I'm like, wait a second, is this what Newton was struggling with? Why was Newton even trying to solve this problem? Well, Feynman says, silly, no, not on this problem, but a very analogous problem. He was trying to figure out the gravitational field due to Earth. See, just like with Coulomb's law, You see, just like Coulomb's law, the Newton's universal gravitational law only works for point masses, which means if you have to calculate the field, gravitational field close to the Earth, you have to do the integral. And that's exactly what Newton was struggling with. For years, he did the integral. It took him years. He eventually did it though, of course. He himself invented calculus, by the way. And he did it, and that was a nasty proof, and whatever that is, he did it. But we can do the same thing in minutes now, or maybe in seconds, actually in minutes. So let's go back to our problem. I mean, it's the same problem. We'll do it for charges because we're working with charges. All right, how do we figure this out? Well, the first step is to understand the symmetry. Because of the spherical symmetry, the electric field everywhere at the distance r will be exactly the same and radially away because it's a sphere, right? And because of the symmetry, what we do is first we draw a closed surface. This is also called a Gaussian surface because Maxwell's first equation, all the things that we did was first done by Carl Friedrich Gauss. So we draw a Gaussian surface, and now we look at the Maxwell's first equation, which is called Gauss's law as well. What will be the left-hand side? Remember, the left-hand side, because we have a sphere, we have to figure out the electric field multiplied by the tiny area over here and then sum it all up. That's what the left-hand side is. But because this is a sphere, the electric field everywhere is the same. Just like what we did before, the electric field pops out and all you get is the summation of all the areas. That is basically the 4 pi r square, which means the left-hand side just becomes E times 4 pi r square. So look, even though there's an integral over here, when you are using it for a symmetric case, that integral vanishes. What is the right-hand side? The right-hand side is the total charge that's inside that Gaussian surface, and that charge is just Q. And there you go. That means the electric field just happens to be Q divided by 4 pi epsilon naught r square. You get the same result as you get if you had a charge at the center of it. Just imagine how frustrated Newton must have felt after doing all that integral and everything. He gets the same result. Feynman says, well, in his defense, Newton already intuitively knew that the gravitational field should look very similar, but he just wanted to prove it mathematically. Well, so there's one way to prove that. You do all that integrals, but this is also a rigorous mathematical proof. And what I find amazing is that we started with Coulomb's law, but we took a different route. Instead of integral, we went into this and created this beautiful equation, and now we exploited that equation to then get the fruits of it. Isn't that, I don't know, it's this is amazing. Whew. All right. Feynman, do we have time for Maxwell's second equation? And Feynman says, it's already almost done. What? Yes, you can just build up on this and we'll immediately get Maxwell's second equation. All right, Feynman, how do we do it? Well, Feynman says, for this, imagine an alternate universe in which we have positive and negative charges always coming together as a dipole, okay? If they were inseparable, if you always had positive and negative charges together and everything else the same, what would Gauss's law look like in that universe? And I say, well, then whatever surface you choose, the total charge inside will always be 0 because you're always having positives and negatives together. So total charge will always be 0. This is what the Gauss's law would look like. But I asked Feynman, why are we considering alternate and hypothetical universes? Because Feynman says, this is true in this universe as well, not for electricity, but for magnetism. He says that in magnetism, unlike electricity, you do not have a single north pole or a single south pole. North and south comes always together. And our first instinct might be, well, I'll just break the magnet. But we don't. If we break the magnet, we'll again get a north and south. We'll again get a magnetic dipole. And even if you go down to the level of a single electron, it is a magnetic dipole. Which means if we were to now write down Maxwell's second equation, I think you have everything you have. You should be able to write it down. What would Maxwell's second equation be? Come on, folks. I think we can do it. Well, Maxwell's second equation is basically the same thing for magnetism. It says that if you take the magnetic flux over a closed surface, what should that answer be? It should always be 0. Because you only have dipoles. So the Maxwell's second equation is basically telling us that there are no such thing as magnetic monopoles. You only have magnetic dipoles. There we have it. 2 Maxwell's equations down. All by intuition. Finally, before we end, we ask Feynman, but Feynman, we still have a long way to go. What about these other monstrous looking equations? And he says, well, Mahesh, the hard work is already done. We can use the intuition that we've gotten for these 2 equations and use that to build the rest of the equation ourselves and also get the differential versions of it. So all of that will come, but for now, just reflect, he says, on how we arrived at it and be at a position where these equations no longer seem like mystery. These equations should be talking to us directly. And hopefully you can now see how this is just the Coulomb's law, but written in a much more beautiful and much more elegant way, which is so much more powerful in certain situations. I'll see you. How was that? I don't know. A lot of equations, a lot of excitement. I don't know how it went.